So let's continue. Let me bring back the PDF file. So basically, so we calculated the elastic modulus. Now we want to do probably an even more important calculation here. And so this is the first part of the calculation is very similar to the calculations we did in the case of carbon nanotubes. So basically, if this was one tablet and this was the other tablet and we had the mortar in between them, we realized that these two far ends of the mortar are experiencing the highest shear stress. And so whenever they reach the tau f, so remember, we're gradually starting sigma 0. So this is our variable. We're gradually increasing that. And as we increase that, the stresses in these regions, the shear stresses go up. At some point, they reach these values, and that's when the elastic limit is reached at those points. So after that point, when you increase sigma 0, these parts will deform, the mortar in these parts will deform plastically, and everything else will end here and here. And these regions in the middle will deform these regions will deform plastically, and regions in the middle will deform elastically. But regardless, this end and this end, x equal to 0 or L, is where the the shear stress is the highest. So those are the places where the failure will start. So in equation 6, I put x equal to 0 or L. Both of them will give me one answer, which is this for the shear stress. This is my tau max. Happens at these two ends, and I put it equal to tau f. And so that gives me sigma 0, C for critical. So C for critical, that's the amount of sigma 0 it takes to start to plastically deform, induce the first point that deforms plastically. And I can just rewrite this equation. It's equation 9. I can rewrite it. And so basically, the way I rewrite this equation, the whole point is to have this ratio that is here, also have it here. Okay. And so the amount of force is going to be equal to this guy times the area of tablet 1, because this is the stress that is in one of the tablets. So that is sigma 0 that was applied at the far right of our boundary of the boundary of tablet 1. And so this is F max. I can easily plot this F max, and I can compare this with the ideal case. Now, the word ideal has to be defined, but now with the background you have from carbon nanotubes that we studied, you have a good sense of it. Basically, you remember in the carbon nanotube structures as well as here, the shear stress is not uniformly distributed. But if it was uniformly distributed, it's a big if that doesn't happen, but if it was uniformly distributed, the total force that I require to break this interface is tau f times L. The total force that I would require to basically deform all the points plastically, because L is this, and this tau is the shear stress that is here. Shear stress along the interface. So when I rewrote sigma 1, I could, by taking these two here on the right side, I basically got my ideal junction strength, and I can plot that as a function of ideal case, and you see that it scales like that. So basically, this is the same, very similar concept that we explained in the case of the carbon nanotubes. And the message here is just like last time, that if you that if the overlap is too long, and long is defined by comparing everything with 1 over lambda, then the shear stress is not going to be uniform. So the failure will be progressive, starting from the two ends going towards the middle. However, also I want you to keep in mind that although sigma f max over f ideal goes down, in principle, the value of f max always goes up with L, although when L is very, very large, the incremental increase in f max by increasing the length of L is going to be very minimal. Okay, so basically, just keep in mind here, for instance, that if L goes to infinity, this term approaches 1, and the stress, that the critical stress, become independent of L. So force always goes up with L. So if I want to complement this graph to avoid any confusion, I have to say that the value of F max by itself goes up, but asymptotically reaches a finite value. Now, the other thing that's very important, which we have to calculate, so we calculated the stiffness, strength, and the critical or the yield stress, the force that initiates plastic deformation. We also need to calculate elastic energy stored in this guy. And elastic energy here, what we calculate is elastic energy density. This is energy per unit volume. Instead of sigma, I can put sigma 0c. Epsilon is the epsilon effective. And so the half of the product of a stress times the strain in the elastic limit is elastic energy per unit volume, or elastic energy density. Okay, elastic energy density. So it's per unit volume. Now, if I put the value of sigma 0c, sigma 0c, the critical value of sigma, it's the maximum energy I can store in this guy before it starts to form plastically. And it's just this replacement of equations we had before. You get an equation like this, where the function f, is defined here. And now it begs the question, at what, so this f lambda L is a function of L. So it begs the question, at what L does the elastic energy density will be maximum? Let's just pose this question, and later on I'll compare it with data. What L will maximize energy? If you go back to this, the first part of the equation doesn't have L. So F has to be maximized. So basically calculate the derivative of this guy, set it equal to 0. And that gives us an L star. So F becomes maximum when Z is equal to lambda L is equal to 3.28. From here we can calculate an L, which we call L star. L star is 3.28 divided by lambda. Lambda, keep in mind, has material property in it, has the width of the tablets in it, has the mortar width in it. So it's a very definitive parameter of the system. And keep in mind, we didn't know lambda until we did this analysis. So now this energy density is a very important concept. It means I can supply this much energy, and if I let go of the force, the guy goes back to its initial shape, up to this much energy. It can take up to this much energy and go back when the force is removed because it's elastic, okay? So now I'm gonna stop this video and I'm gonna continue in the next one.